Afternoon is by Jérémie Bouttier, who is going to give two talks apparently. So vacancy localization in the square diameter model, that's one, and statistics of geodesics in large quadrangulations, that's the second.
Yes, so I'd like to thank the organizers for the invitation. And actually, the reason why I want to give I'm going to talk about two unrelated subjects, and the reason why I want to do that is that initially I was thinking about talking about a paper I did last year about the square diameter model, which is not something I'm usually very expert in, but it was my first attempt at finding new problems in this well-known subject. So I wanted to talk about that so that maybe people here would be interested and maybe spark some discussion. But then I received an email from Bertrand, who told me about the importance, the significance of another project that I did last year too, which is a bit related to the talk of Jean-François Le Gall this morning. So talking about statistics of geodesics in large quadrangulation. So don't look for the connection between the two, because there is none really, except that it's probably examples of problems inspired by combinatorial statistical mechanics. So the first part is about this problem, which is based on a paper in collaboration with Marc Bowick, Emmanuel Guiter, and Manuel Zheng from Saclay and Syracuse University. So reference is there. So it's just well, a new, maybe an incursion in a venerable subject in statistical mechanics, the diameter model, which is arguably as well studied as the Ising model. So it's really archetypical of the kind of combinatorial statistical mechanics flavor problem. And it dates back to, well, very famous, well-known names like Castelline, Fisher, Temperley. And here we study even one of the most known avatars of this model, which is the square lattice model. So it's you have to think about a square grid, or maybe a finite graph, which is a subpart of a 2D lattice, and which is covered with dimers, or depending on how you see them, dominoes, covering two neighboring sides. And here we consider the case where the square lattice is fully covered with dimers, except possibly for a few holes, a few vacancies. So in this model, actually, we begin by beginning of a few is 1, so here we consider the model with only one vacancy. You prefer? Yeah. Okay. Well, here it's in red, so probably. Okay. One vacancy. Depends on your taste. So, well, so in this problem there is a natural notion of movement of dimers, because once you had a vacancy, well, very naturally you would like to think about the dimers as moving and possibly by taking the place of a vacancy, sliding into its place, so that the vacancy would move here. So maybe you know this rush hour game, so it's a bit like the basic idea. And so in this configuration, you see that there are three possible moves starting from this configuration, which corresponds to sliding these three dimers. And this one is not allowed to move because you will need to rotate, and this is not an allowed movement. So, here you would have three possible moves. So, for instance, if I apply this move, then the new configuration would be this one. So, the kind of questions we
have a question. So, the fourth move that you said is not allowed. Actually, it would make sense to consider that also, because
sure.
If you flip, it would be in some sense more natural. It would be uniform. But you want
yes.
this rigid sliding.
Yes, which is yeah. This is my model anyway. So it would be a generalization, and what I would say would probably break down. So I won't. That's.
Have configurations that is totally frozen.
Yes, I will talk. I will show that. So. The question we want to ask is, if we start from an initial configuration of dimers and one vacancy, what can we say about the different configuration of dimers that you can reach by doing a succession of these moves? And well, of course, the typical question is asked is, what if the initial configuration is itself random? Well, it's random, for instance, taken uniformly in the class of configuration of the dimer model on a finite lattice. So here, of course, we don't want to ask questions about convergence to infinity, except in the end. So we begin by considering a grid of finite size, and but later we take the size to be infinite. And well, first thing you immediately realize is that if we consider the case where there is only one vacancy, then of course the number of sites in the grid must be odd. So if it's a rectangle, it would be some of the form 2L plus 1 times 2M plus 1. And another constraint is that the square lattice, it can be naturally be colored in black and white by alternating colors on every site. And well, you see that if every dimer covers one black and one black site. So if there is one more white site than black if you color the corners of the grid white. So the vacancy must be on one of the grid. And another thing that you immediately realize is also the most that you can do by moving around the vacancy is that it can move, of course it must remain on this white grid, but it is confined to one of the two subgrids, because you can also divide the grid, the lattice of white sites into two, the even and the odd lattice, and you see that every move, by every move, the vacancy jumps to by two sites, and it can never go in this the other sublattice of opposite parity. So at most what you can do is reach every other site of the white grid. So what we call even and odd white subgrids, and by convention we say that a corner is even. So, well, a first quite simple case is the case where you start with a configuration where the vacancy is initially in a corner of a grid. And actually, this case is in dimer models is well known because there is a bijection between the dimer configuration on such a grid where you remove a corner, so that means the vacancy is there, and spanning trees on L plus 1 times N plus 1 grid. So it's a grid, it's half a grid, and actually it's the white grid of the even white grid of the model. So
I think this result also holds if the vacancy is on the boundary.
Yes, exactly. I will. Yeah, sure. You can extend that to this case. So here is how the bijection works. So you start with a dimer configuration on a grid and vacancy. The vacancy is here in the corner, and you consider every site that is in the same sublattice as the vacancy, which will become the root. So that would be every other white site. So that would be for instance, all the white sites in the first line, no white sites there. And then for every of these sites, you just keep the domino that is covering it, because you know that there is one. And then with this, the domino is actually covering one of the edges. And so if you put some arrows, you put arrows that are oriented from every white side in the direction of the domino. Then the object that you find is a tree on the half grid, on this grid. And well, okay, it's not very complicated to see that it is indeed a tree, because out of every vertex there is one outgoing arrow, and it's not possible to have loop, because if you count what is inside a loop, you would find that it has an odd number of sites. If you had an arrow, then it would contain an odd number of sites, and this has to contain a dimer configuration and no vacancy, because it is here. So it's not possible. So in the end, what you get is a spanning tree of this grid. And actually, what you realize is that the spanning tree encodes all the information about the allowed moves of the dominoes. Because, for instance, in this case, you would be able to move the domino in this place, and then the vacancy would move here. And then you would continue. And it's not, for instance, here, if you go back, there is a dimer, but it's not retained by this construction. So, and actually, it means that you quickly are convinced that it's because it's not allowed to move into the vacancy. And actually, well, the interpretation of temperless bijection is that if you start with a configuration with vacancy in the corner, and actually anywhere in the boundary, then the spanning tree that you associate by a temperless bijection can be seen as the graph of attainable configuration. That is every site in the spanning tree. To every site, I can associate a unique configuration that is associated to that I can attain from this configuration by moving dominoes. There is a unique way, well, not doing any trivial moves, to move a vacancy here, and all the rest is fixed.
Sorry, I don't understand that if you move, for example, the first two top horizontal divers.
This one and this one.
And then you can move the one vertical below. So
No, you can't move.
why?
No, because there is a, if you come back, there is a domino that is blocking here.
Ah.
You see that there is a... Well,
Okay, okay.
well,
I understand.
actually,
Took picture to
in the construction, the moving the vacancy around amounts to changing the sign of the arrows, because all the arrows flow to the root in this construction, and if you moving the vacancy just amounts to changing the position of the root, but not changing the spanning tree. So okay. So I will say that the vacancy is fully delocalized, because actually it seems to be a complicated problem, but with that you can show that the vacancy can go anywhere, into a maximal number of sites that it can possibly reach.
So the dimers that you eliminated, they form the other spanning, the dual spanning.
Yes. Yes, this will be quite useful. But actually, yes, sure. There is the dual. If you want to do the reverse construction, you have to consider the dual tree, and you realize that there is only one way that the dual tree can be covered with dimers consistent with the boundary conditions. So, okay, that's what I say. So now this property breaks down in the general case where the vacancy is initially in the bulk, because we will see that it can be localized. So here, for instance, here is a configuration with a vacancy in the bulk. Actually, I make the hypothesis here that the vacancy is still in the what I call the even white grid. So that means it would be with two even coordinates if I take the corners to have even coordinates. So in this construction, I just follow the same idea, and what I find is by just retaining every white site on the white grid, that well, I have dimers, but then if I draw loops, I see that now I have loops that can wind around the vacancy. And actually, you quickly realize that the vacancy is allowed to move only on the connected component that contains the root, because you realize that there is a co-cycle in the tree, a dual cycle that is made of dimers that forbid the vacancy from going out. So this is the construction, and so the kind of object that I introduce here is just well, it's almost like a tree, except that it has possibility to have loops that or cycles. The cycles must go around the vacancy, because you're.
The innermost component could also already contain the cycle.
No, it cannot. No, actually, the definition is here. These more general objects, I call them webs. So a web is a grid. On a grid is a spanning subgraph with a distinguished vertex, what I call the root. It comes from the position of the grid, and it makes of the characterization is of its connected components. So there is a tree component that can contain the root, and every other component which doesn't contain the root must have exactly one cycle, and the cycle must wind around the root. So here the tree component cannot have a cycle, and every other component must have one cycle, exactly one around the root, and maybe some bending branches.
So you are saying there never can be a loop that is not surrounding the...
No. For the same reason as the temporary bijection works. And with this dimer configuration on a grid with vacancy in the case of even white grid, it gives what I call a web on the subgrid two times less sites. And you can also realize that a web. What webs have more than trees are the possibility to have cycles. And if you have, it's not a one-to-one correspondence, but when you have n cycles, you have 4 to the n corresponding dimer configuration. And this is you see that by looking at the tree together with its dual tree. And with this construction, if the dimer configuration, also to get dimers, I must put also an orientation on every side such that every site has one outgoing edge. And you realize that there is exactly two possible choice for the cycles winding around, for the black cycle which come from the tree and the red cycle which come from the dual tree that wind around. And you see that there is one more. No, in this case, when you have an even wide grid, there are exactly as many cycles as dual cycles. So that's 2 times 2, 4 to the n dimer configurations. So this property is true for vacancy on the even wide grid, but you can also consider extension of this construction to the other things. But you have to change boundary conditions. But we just consider this case here.
But you could have one vacancy on each cycle. It could be a model where you have the trees. So say
if you allow for several vacancies, it's a more general model. Yeah, it becomes more complicated, and you would find a lot of possibilities. But
you have a determinantal formula for counting.
Yes, you're going too fast. So now what I mean that the graph of animal configuration now just corresponds to the central tree component. They are the only sites accessible to a vacancy, and there is a unique again. If you take a site of this tree, there is a unique way of there is a unique succession of move that brings the vacancy from here to here, which is to the moves along these edges. And so I claim that there is localization, and this tree component is not equal to, in general, to it does not contain. It's not a spanning subtree. It is just contains a finite number of sites, and well, the game is just to say how big it is, and S is the number of sites. So I just state the results. So it's I will talk about the thing. So in the limit where you start with a vacancy in the bulk and take the dimensions go to infinity, well, you realize that in the almost sure sense, the number of sites in the tree component remains finite, and so it's what I call by localization. And there is a limiting probability distribution for S, which is normalized. But it's weak in the sense that still S is a random variable, and it has a power law tail. And we find a critical exponent associated to it, which means that it has an infinite expectation value. So in average, the number of sites is still infinite, even though it's finite. So also a few things that we have been considering is a dynamical property. So if you start from again a random initial state like this, and you do random moves, you give yourself some sort of Markov chain on the state. So it can just be a random walk on the tree components. Then you are interested in knowing how far the vacancy can go, and this we have done numerical simulation on that, and we have found a diffusion exponent. So that would be, for instance, after time t, whatever the dynamics that you choose, the number of sites that you visit. Well, you do a double average, a quench average. So first you average over all possible. You fix a random configuration, and you consider the bar average over all for a fixed configuration. Then you average over all possible walks, and then you do the average over the initial configuration. And then you would find a graph for large t. There is an exponent that we have been able to measure like this. And also another measure would be the mean square displacement. There is another exponent, so we don't really know if they are equal, but it doesn't rule out this possibility. And this is t is time. So you imagine you have a discrete dynamics or whatever. And this is for the vacancy in the bulk. But if you start with a case of a vacancy in the boundary, when we find different exponents which correspond to the diffusion on spanning trees, and we get these values. So well, the method.
How do you start the configuration? You take an exactly sampled one, or do a Markov chain for sampling the initial dimers?
We talk. I will tell that in two seconds. So the methods that we use. So first we want to study the static properties and not the dynamics. So this we've done with studying the problem on finite grids and do some finite task scaling so that we are able to and here we use determinants because it gives an exact way of doing quite efficient way of calculating exact values of exact partition functions, and then you can use convergence accelerating techniques to get exponents, and it works quite well. Sorry? It's a matrix tree theorem. And numerical simulation, then for dynamics especially, we simulate an initial state according to the uniform measure, where you fix possibly the position of a vacancy. And we have tried two different terms of algorithm. So one inspired by the Prop-Wilson cycle popping algorithm. So it's a perfect simulation of. We know that we start with a configuration that is perfectly simple according to the uniform measure on dimers, and also some with different boundary conditions for just consistency. We tried another by more heuristic algorithm. And I want to emphasize that nothing that I say, almost nothing, is rigorous and exact. So it's there are a number of open questions. So yes, I probably know. I want to talk about the the methods that I use, but then the basic remark, I won't spend too much time on that, is that the spanning trees that that you use if you want to enumerate dimer configuration on a grid with vacancy in the corner. As we have seen, this is in bijection with spanning trees, and then you want to count spanning trees on a grid, and then it's very easy to do by the means of a matrix tree theorem. So, which I state as this: the number of spanning trees on a site I naught on a graph which is supposed to have finite size is given by well, any minor, but in particular you could take the minor of a size different from I naught, where the Laplacian matrix is defined like this: -1 for every neighboring site, and it has every row must have an entry 0, so it's the same. It's the degree of a site in the graph, and 0 for non-connected site. So I won't go into the proof, but there are many proofs of that, of course. And there is an easy proof written by expanding the determinant into other permutations. So, for instance, you realize that expanding the determinant, you would get two different types of terms that correspond to non-trivial cycles and fixed points of the permutation. So, for every non-trivial cycle, picking one contribution amounts to picking an outgoing edge of the vertex. And for every the graphical representation of the diagonal, the fixed points of the permutation is also, because it's the degree, you say that you have to pick also one outgoing edge of every vertex different from the root. And what you get with the construction is just a collection of orientation or marked edge on your graph, and possibly there are loops. But then if you collect all the configuration, you realize that the blue loops that come from the diagonal parts get a -1 compared to the red loops, and there is a cancellation for every loop. And in the end, you just get configuration made of arrows which have no loops, and these are just spanning trees. And with this idea, you can easily quickly see the extension to spanning webs. It's done by introducing a line, a defect line. So you would start from the site that is going to become the root, and you take any line that connects to the outer face, and then you give yourself an orientation of lines, and then you modify the weights for the diagonal terms of the edges that cross this of the Laplacian for corresponding to the edges that cross this line. So you would instead of 1, you get -a or -a and -1 for depending on the direction. So it would no longer be symmetric, but still by just doing a counting argument like this, you would realize that you allow for cycles that wind around the root, and there is a global weight which is 2 for two possible orientation, and 2 possibilities for winning cycles corresponding to this global weight. Okay, I won't explain that too much in detail, but it's, well, I think it's quite a well-known idea in physics, actually, how to this modification of a determinant. So here what we have is you need to specify, as I said, there is a correspondence between spanning tree, between webs with n cycles and dimers with up to a 4 to the n factor. So that corresponds to weight 4 per cycle of the web. So it corresponds to putting -1 instead of 1 as the modified weight. So, well, here now we do computation for specific case of dimers on a grid, square grid, and the vacancy is in the middle, and you suppose that it is on the even lattice, so it has to be, the total size has to be this. And then you are able also to further decompose your, you have to compute the determinant of the modified Laplacian that I introduced, and you realize that there is a symmetry, so you can actually block diagonalize the Laplacian, and that amounts to taking only this part of the grid and putting some modified weights of. So you actually what you need to do is to compute the determinant of Laplacian on this grid with different weights. So this is the PL of alpha would be the determinant of the Laplacian with weights alpha in that direction and alpha -1 in that direction, and you would realize that you would have this factorization. That counts just actually symmetric webs. And with that, it's quite, you can just determine it, you put it in Mathematica and you compute it up to some quite high size, because then you realize that would be 241 dimers, the dimension of a square would be this. And we have no real interpretation, but here is a conjecture that is written in the paper about could there be direct interpretation of these quantities. So here is just a plot of the coefficient, there is a scaling curve, but more. Bob? Okay, I won't. I will leave it because it's not related to my subject. Show it to you. We expect the asymptotic behavior of this polynomial to have this form with an entropy term, boundary entropy, and an exponent for L going to infinity and fixed value of alpha. And this, well, you realize that for alpha equal more or less alpha equal 1, that corresponds to spanning trees, and we have a known formula for the entropy of spanning trees on a square grid, and these are given by these numbers. So in our numerical case, what we do is just we take the values that we have computed up to 60. We have the exact values, but then we can use some you can compute an estimate for this entropy, and you see that it converges very quickly by doing some just accelerating the convergence. And so with this technique, you can not only compute the entropy, of course, which we knew this value, we knew the subleading term corresponding to boundary, and then there is a critical exponent gamma tilde of alpha, and this we can compute estimates for it, and with quite a high precision, and very obviously you can see these exact values that we can conjecture. So here are the plots, so you see that there is a very good convergence. And this is consistent with this analytic expression, which is quite reminiscent of Coulomb gas technique. So, okay, this is also conjecture, and then you can try to show it some way. Here is the plot of the estimate versus the numerical data that we have. Well, if you want to go back to this was for PL, which was an intermediate quantity, but if you go back to the partition function, then you can of course deduce the asymptotics for the partition function of webs on a grid, with y being the weight per cycle, so there is this relation, and if you put y equals 0, you would get 1/2 the exponent, well, the known exponent for trees, and then that would be for 4, you would get with this exponent, we get 1/4 for dimers. And so if you, actually you can have an interpretation of these quantities, this ratio between two partition functions, the ratio of the number of trees in the grid divided by the number of dimer configuration with a vacancy in the middle. It can be interpreted as the probability that the vacancy by starting from the middle can reach the boundary, because once you have reached the boundary, you know that you can go everywhere, because it's then you know that the graph that you are considering is a spanning tree, so that is a spanning one without loop. And you see that this quantity goes to 0 as the size goes to infinity. So it's an indication, I would say, that the vacancy cannot, when you take the size going to infinity, the vacancy cannot reach every site. And another indication is that when you can, using this, you can also compute an observable that is the average number of cycles in a web, and this grows logarithmically as L, so that would mean that in the large limit there is always at least one cycle, and I recall that cycles are the things that prevent the vacancy from going to infinity. So with that, well, you conjecture that the prediction is that the tree component in a random web accessible to the vacancy is always finite, and it has some probability distribution, which is normalized, so it's a bit like percolation. And well, if we want to go further, we have estimated this probability using the Monte Carlo methods that I mentioned with different techniques, and well, we find that indeed we get finite values for P of S for finite S, but we also find the critical exponent with which it decreases, and it's consistent with the value 9/8. And you can relate that to the 1/4 that I was mentioning by a scaling argument. So here is the numerical data, and you make a fit to compute this delta exponent. And just in particular, there is a finite probability P of 1 that the vacancy cannot move at all. So really, there are dimers that block it and prevent it from moving. So that was this kind of configuration. You would have dimers. You would have dimers that no one can move, and the vacancy is completely jammed. And so, well, when we go back to the determinant expression, and by just modifying it, we are able to compute the determinants for configuration in such a jammed state. And with the convergence acceleration technique, we are able to get with just 40 up to L equal 40, we get something like 20 digits. And while using proof inverters, we have been able to find this exact value, which is a bit surprising. Well, for the probability that there is only one move allowed, so that would be that instead of having this configuration, you would have just one dimer that can slide into the vacancy and no more. That would be a configuration like this. So we get this value, and we have not been able to guess its thing, but well, recently this was intended to be a conjecture and maybe a challenge for people, but there has been derived in some formalism of Toeplitz matrices by these people. There is paper in and they also address they can derive also over critical exponent, and they are not joking because they have been able to get this value. So I don't think I don't know if I'm a bit reassured that I was not too bad not guessing this.
Can we say that all of these kind of finite blocking probability must be of the form rational plus square root 2 rational?
I have no idea. If you are able to prove that, that would be very interesting.
This is somehow natural because the green function on the square grid only is
yes, maybe. Yeah, sure. But the green function for the translation invariant problem is you need to convert it into. It's not easy to translate it for correlation with only one vacancy, one monomer, and monomer correlation. It's a quite difficult problem, and also these people have been able to somehow adapt some known techniques that were used in the Ising model just to compute a few correlations in some specific direction. So in some sense, they introduce two vacancies that cancel each other, and they take one to infinity. But then you have a very they use a fairly recent math theorem to prove that on the Toeplitz determinant. So
for example, the first one is not an easy combination of green function near the origin.
I don't know. Well, I can show you a paper. I do not understand everything.
But for the first one, you actually don't need to go to infinity because it's just a local configuration. It's equivalent to having 9 monomers missing, right? Yeah. I mean, you have a choice of 2. You have 2 choices for the boundary, right? One is the one you draw, and there's another one, and then it's exactly as if you had 9 monomers missing. So you don't, I mean, it's just a local configuration.
It's a local, but I don't, okay. I'm not an expert, and I don't know really how to compute local correlation involving one monomer. I know that there is a whole theory for dimer correlation, but one monomer, I don't know.
I mean, if it's just two monomers that are not far from one another, you just do similar thing to
Yes,
what you
that's
did.
that's the idea of
Perturb the Pfaffian.
yes, that's the method. But here you have only one, and the other one you have to get rid of it. So you have to take it to infinity. So you have to perturb your determinant by at least by infinite part. So okay, but maybe I will leave that for later discussion. And just to show to conclude on this subject, we are also, as I said before, by simulation we have studied the diffusion on spanning trees and webs by numerical simulation, and we get these. Recall these values what we have, some corresponding to trees, so that would be also webs with no cycles or dimers with vacancy on the corner on boundary, and this would be for vacancy in the bulk. So what we, well, just how the numerical simulation look like, so by doing sufficient enough samplings you get really small error bars, and this you can do fits and you can safely get the exponents. So what we get is, well, we can predict that these two are equal, which is not very surprising. The relation between the tree and web exponents would be some scaling relation like this, which is, you can see by a crude scaling argument saying that essentially the diffusion in a web, it looks like the diffusion on a tree for small times, and then at some point, because the tree is finite, and the rate at which the tree is finite is given by probability distribution of S, then it saturates to the maximal value S, which is the maximal number of sites that you can visit. So by doing an estimation of that, you get this scaling relation. And well, less conclusively, we can guess also exact values, and I have no idea if anyone has written this or proved anything on the diffusion on spanning trees, which is quite a simple exponent.
Diffusion on spanning trees, it must be somehow related to the fractal dimension of the chemical paths on the spanning trees, right? Which is 5 by 4.
Probably, yes.
So that's why it can.
Yes, probably that can, and then this would follow. Okay, but that's so. This is my the end of this talk, and so as a conclusion, we find a weak localization for the vacancy, and because the vacancy, if the localization was strong in the sense that P of S would have exponential decay or something, you would not get an interesting diffusion exponent for that. So okay, this is something, and okay, nothing is rigorously known, and there are connections to combinatorics and open question there, and okay, there are at least a few possible directions that I not really delved into that are. Interaction between several vacancies and the other lattices. So for instance, in triangular lattice, which is not bipartite and the temporary bibation breaks down, we expect a completely different behavior, and that would be strong localization. There are some recent work, numerical works showing that. Okay, so let me now quickly jump to the second talk in 20 minutes. Talking about statistics of geodesics in large quadrangulation, but this one is, it will be easier for me because this has been a bit introduced this morning by Jean-François Le Galle's talk. So you are supposed to know what is a quadrangulation. I don't have to tell that. So what we do is we consider the random planar quadrangulation. And random, I mean we take the uniform measure on quadrangulation of finite size. And in the end, you want to, the size go to infinity, and you want to study statistics of this quadrangulation in the sense of that you view a quadrangulation as a, as we say, the discrete random surface, and essentially that would be a metric space because quadrangulation is like a graph, and you have a graph distance. And what can you say about that? So this is an old subject in combinatorics and also in physics. So the quadrangulation and the question of enumeration of maps, these are known, and the real progress from this, as we told this morning, came during the thesis of Gilles Schaeffer, and introduced what is known as the Schaeffer's bijection, because it's a bijection between quadrangulation and trees, and this bijection contains enough information about the contains some information about the metric properties of quadrangulation, and then you are able to extract information out of that. And it's called Schaeffer bijection, but I don't. It's really unclear where it has been first published, because it has been first written in a paper by Marcus and Schaeffer, but which is still an evolving manuscript. And well, the reference, maybe the first reference was a quotable reference is Chassin-Schaeffer's paper in 2004. And it's different between. It's slightly different from the first bijection between, because okay, you have two classes of objects that are in correspondence. So bijection just means basically that it has the same number of elements. And but the original bijection found in the 80s by Corey Vauquelin did not carry that much information on the geometry of quadrangulation. So just to say, what I'm going to follow is a complementary approach to the approach of Jean-François Le Gall, with more trying to define characterize the continuous limit of quadrangulation. Here I first state some results on the enumeration, discrete enumeration of some classes of quadrangulation, and then find exact partition function or generating function for this object, and then I will in the end maybe take the continuous limit or large distance limit that could be related to the continuous approach. So just to give you a reminder, maybe, or maybe a different viewpoint, what is Schaeffer's bijection? It's very elementary. So it's you start from a rooted planar quadrangulation. So I hope that you know that is. I will show an example of quadrangulation in 2 seconds. That has a root. So a root is a choice of an edge that is marked and oriented. So it's useful to avoid symmetries, possible inner symmetries of quadrangulation. It's a classical step in the enumerative theory. And then, well, you see that the information that you code is you will to each vertex of the quadrangulation you will assign a label that is the distance. It's the graph distance from the origin, and the origin being the vertex at the origin of the root edge. And maybe I will show just quickly an example. So this is a quadrangulation. Ignore the dotted lines. So okay, it doesn't appear very well, but this is a graph embedded in the plane, and all the face. So it's not very visible, but every face has degree 4. And if you study what happens around each face, which has degree 4, you realize that there are only 2 possible configurations of labels around the face. So for instance, there is an eye that is a minimal label around the face, and then you realize that because the labels are not just taken at random but are really distances, then the label can only vary at 1 or -1 around each edge. So in this case, if it's minimal, it must increase in that direction. It must always change and not remain equal, because a planar quadrangulation is always bipartite. So the distance increases by 1 modulo 2 along each edge. So and if I is the minimal label, then the only freedom is the label of the opposite vertex, and then you have these 2 possible choices, and Schaeffer called them simple and confluent faces. And then you apply 2 basic rules to get a tree, because the bijection involves trees, and you put these blue lines. So in one case, you just keep one edge of the you have one edge of the original quadrangulation. So here you must be careful that this involves the orientation of the surface. So it's really you take this you have an orientation of the, so you have to take one convention, which is this one, and this one you take you add a new edge to the quadrangulation, which is a diagonal edge. And so in this example, so I applied these rules to every face of my original quadrangulation, and then I retain some edges of the quadrangulation, and I create new ones. And then you see that the origin remains disconnected, and actually it's not very difficult to prove that the object that you get is a tree. And furthermore, it's a well-labeled tree, because you see that the label can increase by 1 or decrease by 1 depending on direction, or remain the same. And so the labels are here. And so this is bijection. There is an inverse bijection, which has been described by Jean-François this morning. We'll briefly show it later. So here I want to consider the question of quadrangulation with a marked geodesics. So you could apply, of course, to, if you take a quadrangulation and somewhere you imagine that it has a geodesic, and then it's a quadrangulation, so you can apply Schaeffer's bijection. But then the problem is that, in some sense, you lose the information about that geodesic, because it can be cut in some parts, and it can be information that is diluted in the tree. So there is just a simple trick It's easy once you have found it. It is how to retain the information about the geodesic that you mark in the bijection. So you take a geodesic and then you split it into two copies of it. So it's as if you unzip, or you take a surgery tool and you cut inside the edge, and you split every edge of the geodesic into two things. And so you create a new face that has, if I is the length of your geodesic, you create a face that has degree 2i. And then this is not a quadrangulation, but you can make it easily a quadrangulation by putting. You have to choose one direction. So in that case, you would create diagonal edges so that you preserve the distances. So you create a new quadrangulation out of the original one, and it has the same labels for vertices. And then you apply Schaeffer's bijection, and then Schaeffer's construction, and then you realize that, well, for the new faces, well, outside what it's not represented here is that outside you have a quadrangulation with faces. You apply the rules in every face. And for these new faces that you created, you realize that you are exactly retaining these edges. So in the end, by applying, you get a tree, but it's a special tree that has what we call a spine. So there is it is rooted at a label 1, and there is the orientation matter. So it's a plane tree, and in this case, that would be the rightmost branch must have increasing labels from 1 to I. So we get to a spine tree. So actually, it's not completely a bijection. You have some subtlety that I will just quickly mention, is that you don't obtain all spine trees this way. So we would say that a spine tree is a well-labeled tree with just this property that it has the rightmost branch is increasing labels. And you realize we saw this morning the inverse construction by inverse construction is that you have to recreate the original quadrangulation. You have to consider every what we call corner of a tree, so that is a vertex can be is visited as many times as it has outgoing edges, and for every corner you connect it to the closest vertex connected with label exactly below. So, for instance, you would have a vertex with label j plus 1, and for every corner you are looking for the first vertex that you encounter which has label j. And the obstruction in this case, or the failure of the construction, would be that it would be possible that the part below, all the vertices in the part below the tree would be all higher than j, strictly higher than j. So in that case, the next one would be, if you draw what we call the chord, that would be the new edge of a quadrangulation. You would connect it in two ways. And in the quadrangulation, remember that I split my quadrangulation in two. That would correspond to a case where here, by this construction, you always obtain a quadrangulation where the two copies of the geodesic are distinct. And here you would have a pinch point, what we call a pinch point. That is a common point between the two geodesics, and this is not forbidden. So, but well, okay, it's just because you have not taken a general class enough, and that would be the case that the objects that we're really dealing with are just quadrangulation with what we call a geodesic boundary. So it's not a quadrangulation, it's just all the faces have degree 4 except for the outer face which has degree, higher degree, can have a high degree, so it can have degree 2i. And the constraint also is that the labels on the outer face are these ones, which means that the two sides of your face are actually geodesics. And this with this you have a bijection. So this is what I state here, and then okay, you can quickly see the link with if you want to see the link with the original question of having a geodesic, a marked geodesic, then you realize what you are interested in are just so here you would have a quadrangulation with a geodesic boundary, and but it possibly pinches at some points, and then you are just interested in some irreducible part of your quadrangulation. So to go from this to this, you just have to take some sort of connected component, and this can be easily translated into a recursion equation for. So this I'm going to write. So if you want to do enumeration of these objects, so the basic object that you want to enumerate are well-labeled trees. So for well-labeled trees, you can because of the constraint that the labels must vary by 1, 0, or -1 on every edge, you can quickly write a recursive decomposition of these well-labeled trees. So this is okay. This is the equation. So just to understand it, you would imagine that you have a well-labeled tree that is you have a tree and it is rooted at some vertex I, and so it has a root edge like this. This connects to some sort, and then you have possibly other edges here and here. So if you just cut the edge in, you remove this edge, what remains? You have the possibility that, well, actually, you could have in this case, you must allow for isolated vertices, so that would be just a vertex, an isolated vertex, and that would be 1. But if you add at least one edge, then what you get is you get 2 non-empty trees, so one corresponding to this vertex, and one to this, and this vertex is j, with j equal I-1, I or I+1. And then you add a weight per edge, and okay, and then this decomposition immediately translates into this recursive equation. So this equation has a unique solution as a power series in G, and where G is the weight per edge in the tree that you introduce, and corresponding by the Schaeffer bijection to face in the quadrangulation. And I is the label of the root vertex. And so this equation is only valid. Of course, you want the labels to be positive. So this equation supposes that you are considering a label. So this equation is valid for positive I, and then you can it's still valid by taking convention that R naught is 0. And actually, when I talk about the generating function for well-labeled trees starting at vertex I, it's already a small generalization of the notion introduced by Schaeffer, because Schaeffer was considering well-labeled trees always starting with a label 1. So if you want to get out of this equation the original well-labeled trees that correspond to rooted quadrangulation, you would have to get R1. So you have to solve this equation, and then if you want just the rooted quadrangulation, you have to get R1. So okay, this seems a bit complicated, but actually the nice thing, and I'm able to quote the second organizer of the workshop, in a joint work we have been able to compute the exact solution to this equation, where this equation must be understood as an equation for power series in G. And it has this form, so it's a non-Zats, some sort of n-Zats, but you plug this form into this, and you realize that it works, provided that these auxiliary quantities that you introduce, R and X, satisfy this equation.
Is a power series in G?
Sorry?
G is a power series.
Sorry, it's a typo. Of course, it's X. So you recognize this one is quite easy because it's a Catalan-like recursion relation, and there is just a free and corresponds to the free possible choice of the change of label. So R, it's just if you compute the generating of R, it's Catalan numbers, the Cn times 3 to the n, and this has an obvious explanation. X is a bit more subtle, and well, okay, we don't really know what it counts, but still, it's if you solve this equation, you realize that it's a power series with integer coefficient in G, and you plug it, and so this combination is still a power series in G, and this solves the equation. And so this is the exact form for the generating function for well-labeled trees starting at label I, but these are general well-labeled trees and not the spine trees that I've been considering. But it's not very difficult from this picture to count well-labeled trees, because here you see that you have a sequence of vertices, and then what you have below is just a well-labeled tree, one starting at 1, one starting at 2, one starting at 3, etc., up to I. So it's just by doing the decomposition. The partition function is just the product of the RJs up to I, and you plug in the previous form. You see that it's a telescopic product, and you get this nice formula. And now, if you want to, this corresponds to the generating function for quadrangulation with a geodesic boundary of length 2I. And if you want to get the generating function for quadrangulation with a marked geodesic, you have to do this, translate this decomposition in irreducible parts into generating function, and it just you just have to say that a general quadrangulation with a marked geodesic is made out of the first irreducible component that goes up to J. And you have a general object that is like this, then it pinches at the first label at which it pinches is j, and then you have something else, and this is a u, and this is a z. So this is the equation. So once you have that, okay, we don't have an explicit form out of this, but if you go to Laplace transform, it makes things explicit. Another thing that we get for free, well, in some sense, is a more general enumeration for what we call confluent geodesic. So that would be an object that is a quadrangulation with two marked points at distance 0 to I, and instead of marking just one geodesic, you mark several of them. But then to make the decomposition work, you have to assume that they are what we call weakly avoiding. That is, they can touch each other, but they cannot cross each other. And in this configuration, your k geodesics, they delimit a number of regions. So the first geodesic would be this one, for instance, this one, and the second one would delimit a region that is well, actually it's a z. So if you want to consider, you would have confluent geodesics, for instance, on a quadrangulation with a geodesic boundary, and then your partition for the genetic function would just be the I to the k. But then you have to impose that there is no pinch point in the global object, so I don't explain that too well. But this is essentially the same transformation that you apply not to z, but to z to the k. And if you just want to study the really strongly avoiding geodesic, that is geodesics that do not connect each other, what you have to do is you take some objects like this, and you just glue them together, and that corresponds to computing I to the k, and this corresponds to strongly avoiding case. I mentioned these two cases because these have different scaling behaviors. So now I'm going to go quickly in the results, and probably not well. So if you want, once you have the exact solution, how much time? 2 minutes. Okay, 2 minutes. Once you have generating an exact solution, then it's just an exercise. I mean, just an exercise in analysis to compute the large asymptotics of your generic term of your series by just doing you have a series, so you just have to expand around the what I call the critical point, which is 1/12 in the quadrangulation. That means the radius of convergence of this series, and you know that the large n asymptotics of the generic term of your series is related to the expansion of its sum. So, for instance, if you take the quantity zi that I introduced, then it's explicit, and then you can just take this. You expand g around this critical value, and you put this because it's a convenient parametrization. Because if you want to compute what the coefficient of G2Vn in this quantity, you just have to do a saddle point approximation, and okay, it's just an exercise. And with this, it's all explicit, and you get a sequence of rational, almost to the I factor. You get a rational factor. So, for instance, you would get, if you pick the coefficient of G2Vn in this series, you would get this asymptotic form. And this is true for n going to infinity, but for the moment we keep E finite, so it's the local limit of large quadrangulation. So the very natural normalization is just to divide by the number of quadrangulation with 2 points that mark at a distance I. So that would be to count, for instance, the average number of points in the average number of geodesics joining 2 points. So the normalization would be this, because you can identify the terms. So you take out all the extensive factors, and all you get is just a rational function in I. And so it amounts to considering a random quadrangulation where you fix 2 points at the distance I. So just to go briefly through the results. So if you apply this scheme to UI, which corresponds to quadrangulation with two marked, just a quadrangulation with a marked geodesics, then you can compute, you get for, okay, I small with respect to n, but still large, and so it's 3 times 2 to the I, and this corresponds to the average number of geodesics joining 2 points in a doubly pointed quadrangulation. So the confluent geodesics, it's interesting to see that despite the fact that you would think that you take less than you have less than k independent geodesics, still the correlation function is larger than this one to the k. It's because of correlation, so that would be the average number of k-tuples of weakly avoiding geodesics. And you get a different behavior for strongly avoiding geodesics, that is geodesics that do not touch each other, and you see that it when this exponent becomes negative when k becomes large, and so this we interpret as the fact that there are few or rare exceptional points linked by really distinct geodesics. So I just quote a few other computations that you can do with this idea. You can show that geodesics that are have the same extremities but are just constrained to be weakly avoiding, they tend to be common along a large part, and they have a very large number of contacts. So it's proportional to the length of them, third of them. And we can also address questions as separating cycles in this idea, but basically the idea is that they are the same in the scaling limit. So in the sense that the difference between them is negligible, so that would mean that two geodesics, they delimit two regions, because it's a picture like this, you have two regions, and one of them always remains finite when n goes large, because it's of the order I3 where I is finite, and the other one is infinite. And I just mentioned that this is not true for strongly avoiding geodesics. And I don't explain what goes, but we are also especially interested, but it becomes more involved, going to the scaling limit where I becomes large together with n, with this scaling relation, which corresponds to the Brownian map that you introduced. But I must say that all these results remain true. So for instance, even if I becomes large, you still have this relation that holds. So basically we have the same picture for finite and well, infinite, but scaled, rescaled distance n. So to reach my conclusion, so we have been able to study the statistic of geodesics in large quadrangulation. Well, in this way it's more computational, because we have an exact generating function, and we don't really prove that the limiting object exists, but we are able to compute some of these properties. So this proves to be a complementary approach to Legal's approach, and it's interesting to connect each other. And I must say that it's still a bit work in progress, because this decomposition into irreducible part doesn't turn out to be the most fundamental decomposition that you can do, and there is an interesting connection that I'm exploring with HIPS. And of course, so you can, as Jean-François Legal mentioned this morning, you have more general classes on that than just quadrangulation, but we expect the results to be mostly the same, because we are in the same university class, but still that is a direction to study what happens in that. And I strongly suspect that we get exact formula like this. This formula, for instance, I suspect that it remains true for general class of maps. I will stop here.
But essentially with the same technique you could calculate the probability that a geodesic up to distance I, there exists two geodesics reaching I, which are strongly self-avoiding from distance J on.
Yes, I believe that you can do that.
Because this one would be the one which relates to the seminar
Sure.
this morning of the lollipop diagram.
Yes.
So it's not neither exploding nor going to zero strongly, but it will give you some order 1 result. Because you see, the third result is going down, and always as k is larger than 2. The first two are exploding.
Yes, but there is a question of interpretation that is not very clear here, because here I'm computing, I'm dividing by the number of quadrangulation with 2 mark points. So I'm working in an ensemble in some sense, or random quadrangulation that have 2 mark points at distance I. But the results are not, if you want to go back to quadrangulation with just 1 mark point or just general quadrangulation, then you change the normalization. Here I introduce the normalization corresponding to 2 mark points at distance I, and you see that this number grows like I to the 3.
So you cannot
So
read out probability.
you get different interpretation, but you have to put back the I to the 3, and you get different exponents. And well, I think there is a connection with, and actually we are saying the same thing as Jean-François said by putting back. So So the strongly avoiding geodesics, they are rare, already rare in quadrangulation with 2 mark points. But if you just consider quadrangulation with one mark point, well, you have I free to the more points, so you are free to choose your second point, and you can find truly avoiding geodesics. And if you still allow to change the route and consider truly geodesic without roots, you can find 2 specific points where you get 3 of them, and this will follow. But I really think that you cannot go further than that, so 4 points would not be. And of course, there is the question of saying whether the geodesic, as you said, are really strongly avoiding or just strongly avoiding on some part and thing. But I believe that the exponent would not be fundamentally changed. So that's what I say when I say find other observables, because what I found is just these complicated functions are just some observables of your model, and you can think about more complicated ones to do. But everyone is an exercise, I would say.
Okay, let's speaker again.